In this video, we introduce vectors and coordinate systems for three-dimensional space. This will set the stage for the study of the calculus of functions of two variables, because the graph of such a function is a surface in space. Thanks in advance for watching this video. If you liked this video, don't forget to like and subscribe to the channel and activate the bell. It is very important for the continuity of this channel. You should remember that the Cartesian plane is determined by two perpendicular number lines called the x-axis and the y-axis, dividing the plane into four quadrants. We know that any point in the plane can be represented as an ordered pair of real numbers, where A is the x-coordinate and B is the y-coordinate. For this reason, a plane is called two-dimensional. To locate a point in space, we must add a third dimension to the model. We can construct a three-dimensional coordinate system by passing a z-axis perpendicular to both the x and y axes at the origin. Usually, the 3D coordinate system is drawn as follows. The right-hand rule is used to determine the placement of the coordinate axis in the standard Cartesian plane. If we curl the fingers of our right hand around the z-axis in the direction of 90 degrees counterclockwise rotation from the positive x-axis to the positive y-axis, then our thumb points in the positive direction of the z-axis. We call this system the three-dimensional rectangular coordinate system. It represents the three dimensions we encounter in real life. The three coordinate axes determine the three coordinate planes: the xy plane, the yz plane, and the xz plane. These axes define three planes that divide the space into 8 parts known as octants, as shown in the figure. The first octant is determined by the positive axis. Octants 2, 3, and 4 are found by rotating counterclockwise around the positive z-axis. Octant 5 is vertically below octant 1. Octants 6, 7, and 8 are then found by rotating counterclockwise around the negative z-axis. Look at the figure. The three-dimensional rectangular coordinate system consists of three perpendicular axes. the x-axis, the y-axis, and the z-axis, regarding the x and y-axis as lying in a horizontal plane and the z-axis as vertical. Because each axis is a number line representing all real numbers, the three-dimensional system is often denoted by R3. Any point P in space can be specified by an ordered triple of numbers, where x, y, and z are the steps in the x, y, and z directions from the origin to P. Let's see how it works. Plot each point in space. The point 4 minus 3, 4 means x equals 4, y equals minus 3, and z equals 4. To locate the point 4 minus 3, 4, we start at the origin and move 4 units along the x-axis, then 3 units in the negative y direction, and then 4 units in the positive z direction. To locate the point minus 2, 6, minus 4, we start at the origin and move 2 units in the negative x direction, then 6 units in the positive y direction, and then 4 units in the negative z direction. To locate the points minus 5, minus 7, and minus 4, we start at the origin and move 5 units in the negative x direction, then 7 units in the negative y direction, and then 4 units in the negative z direction. Now is the point where I think it best to specify the Euclidean spaces that you have probably already studied, and to give a rigorous definition of each of them, as well as its geometric meaning. R1 is a one-dimensional Euclidean space. Analytically, is the set of all real numbers. Geometrically, is the real line. The numerical value of x gives its position on the line. R2 is a two-dimensional Euclidean space. Analytically, is the set of all ordered pairs of real numbers. Geometrically, points in a plane. R3 is a three-dimensional Euclidean space. Analytically, is the set of all ordered triples of real numbers. Geometrically, points in space. We know that in two dimensions, the solution of a single equation involving x and y coordinates is a curve. Now we will do some examples to see how the graphical representation of some simple equations is in both the two-dimensional plane and three-dimensional space. Let's start with a very simple example. Graph x equals 4 in R1, R2, and R3. In R1, we have a single coordinate system, and so the solution of this equation gives its position on the real line. In other words, x equals 4 is a point in a one-dimensional coordinate system. In R2, the solution of this equation is the set of all the points that are in the form for y. Graphically, the equation x equals 4 represents a line parallel to the y-axis in a two-dimensional coordinate system. In R3, the solution of this equation is the set of all the points that are in the form for y, z. This is the vertical plane that is parallel to the yz plane and 4 units in front of it. Graphically, the equation x equals 4 represents a plane that will be parallel to the yz plane and pass through the x-axis at x equals 4 in a three-dimensional coordinate system. Let's make another example. This equation is in the standard form of the equation of a line. We can rewrite this equation in standard form to be in slope-intercept form. Note, this equation has two variables, so this equation cannot be in a one-dimensional space, since one-dimensional space has only one variable. So we have to throw out R1 for this example. In R2, the solution of this equation is the set of all the points that are in the form x minus x plus 2. Graphically, this equation represents a line with slope minus 1 and a y-intercept of 2 in a two-dimensional coordinate system. In R3, this equation represents the set of all the points that are in the form x minus x plus 2, z. Because we have not specified a value of z, we are forced to let z take any value. So the graph is then a vertical plane that intersects the xy plane in the line y equals minus x plus 2 and z equals 0 in a three-dimensional coordinate system. Let's solve one more example. This equation represents a circle centered at the origin with a radius of 3 units. In R3, however, this may or may not be a circle. Since we have not specified z in any way, we must assume that z can take on any value. The equation represents all possible horizontal circles with no restrictions on z and is therefore the circular cylinder with radius 3 centered on the z-axis. We must be careful to solve part B. The points are on the circle with a radius of 3 units and center on the z-axis at the level of z equals 5. So the circle lies in the horizontal plane z equals 5.